So good morning all. So this is the last day of our lectures. Okay. So tomorrow we would have a field trip. So I am very happy to have Professor Sukanta Roy. He is the director of a borehole geophysics research laboratory in Karad, which is around 150 kilometers from Pune. So we have learned a lot of proxies, lot of archives to track, to trace the climatic variations. So he would be talking about very, very unique and very, not many people know about that. Okay, how actually past temperature can be reconstructed and the variations we can find out. So there is a call. This is geothermal temperature, and they use the actually borehole temperature. So he would explain you how this technique works and what are the advantages of using this technique. Okay, Professor.
Okay, a very good morning to you all. Thank you, Dr. Naveen Gandhi, and other faculty members here, Dr. Murgaonkar, I see a lot of students here. So I'll like to, as Dr. Naveen Gandhi mentioned, I would like to introduce somewhat less commonly used so far method to reconstruct the past temperatures. And I'm with this, I'm not really going to talk paleo, but past in the last few centuries, few decades to few centuries. Okay, and how the borehole temperatures, that is the temperatures that are measured as a function of depth inside the earth, they can tell us what they can tell us about the past temperature changes that have happened in the past few centuries, up to a few centuries. Okay. First, I would like to acknowledge that much of this work was carried out when I was at the National Geophysical Research Institute, Hyderabad. I continue to do this, but a lot of the work that I'll show was done there. And Vyasulu Akiraju is one of my earlier students. So he also participated in this work. Okay, so this is very well known to most of you. I don't have to explain this, particularly standing at IITM, I don't have to explain this. This is the temperature, the average surface air temperature record, averaged over land and ocean, right? And what you see here is starting from 1880 onwards, when temperature records started extensively, meteorological temperature records started extensively, and up to the present, there has been a lot of temperature variations, and sometimes they have remained more or less steady. Sometimes they have increased, then steady, then increased. So in the last, last 60, 70 years, it has been continuously increasing. Now, this is what represents a big part of the climate change that you want to study. And the point that I'll be addressing here is whether this kind of a surface temperature change leaves any signature inside the earth, in the subsurface rock, for example, and how to retrieve that information. Okay. So what's the motivation for doing that? You have all, are there geologists here among the students? How many geologists? Good. How many physics, geophysics, and meteorologists, environmental? Okay, fine. So a majority of you are geologists. Okay. So the point here is, what's the motivation for studying this? Now, if you see here on the x-axis, we have plotted the year from 1500 onwards up to the present. On the y-axis on the left-hand side, we have plotted the carbon dioxide concentration in parts per million in the atmosphere. And on the y-axis on the right-hand side, we have methane gas concentrations in the atmosphere in parts per billion. I'm sorry, this should be parts per billion. Now, if you see this trend starting from about 1500, the curves are relatively flat. The concentrations are more or less flat, unchanged up to about 1850 AD. And after that, there has been a concomitant rise in both carbon dioxide and methane gas concentrations, okay, up to the present. For example, now the carbon dioxide concentration is how much? Can anybody do anybody remember? Does anybody remember? Right. So similarly, methane is also increasing. Now, if you look at another record, this is the surface air temperature record that I showed you in the previous slide. You can see here I think the first surface air temperature record was around 1860 or so, but the surface air temperature record that is available is the same as what was shown in the last slide. Now here, if you see, this shows from 1850 onwards, this shows a gradual rise and then a rapid rise in the last several decades. Now this is this trend is very consistent with the carbon dioxide and methane concentrations in the atmosphere. But this record is about 120 years, the meteorological, the instrumental record of temperature. And this duration, about 100 to 120 years, is too short a time to really compare, to really know what was in the past. For example, whether these temperature was flat, like the carbon dioxide and methane concentrations in the past several centuries, or whether there were epochs. So we don't know, because we don't have a reference. We don't have a 18th century or 19th century reference in order to gauge whether what we are seeing in the past century is anomalous or is it a part of the normal natural cycle. So here, the borehole temperature record can play a role. In other words, what we are trying to find out is, before the start of the instrumental records, what was the kind of temperature scenario, whether it was like this or like this or like this. Okay. Okay, so the outline of my talk would be to explain the solid earth, that is the earth below our feet, how it acts as a thermal tape recorder, tape recorder. So thermal tape recorder. And then how we analyze the borehole temperature data, how then we can also combine the borehole temperature records with the meteorological surface air temperature data. And then if there is still time, we will go into some fundamental issues of addressing this methodology. But here you can see the temperature plotted on the x-axis and depth in hundreds of meters on the y-axis. And you can see that the temperature, increases. First, it shows a decrease, and then it starts increasing in all the profiles. Now, this is not something that you would expect, because as you go deeper and deeper, what would happen to the temperature? It would increase. And that's the, there is a geothermal gradient. That is the rate of change of temperature with depth. And it's a consequence of the upward flow of heat from the interior of the earth. So simple laws of thermodynamics. And therefore you would expect gradually a systematically increasing temperature with depth. But really, when you measure the temperatures inside the earth, you don't get that signature from the start. What you usually get is, you usually get a curvature in the upper part and upper 100, 200 meters, and below 200 meters or so, what you get is this systematically increasing temperature with depth that you expect in accordance with the Earth's upward heat flow. Okay, Fourier's law. So this is the part which is of interest to us in the next 40 minutes or so. Now, you have studied various past climate change indicators during the course of this week, and today I think the next talk is on tree rings that you will study. But you have seen corals, which give resolution of months to years, ocean and lake sediments interannual to decadal, glaciers and ice cores annual to decadal. I'll be talking here about the borehole temperature records, which gives us information on decadal to century time scale. And when you talk about the climate change, it's actually the long-term temperature change, right? Climate change is associated with the long-term change or energy imbalance on the surface of the earth. And the earth, really what it does, it integrates all these changes and perturbs the normal geothermal field in the upper few hundred meters. Okay. So if you see temperature profiles, these are temperature depth profiles actually measured in boreholes in different continents. Okay. Here I am showing one from the high latitude region and another from India. So there are several temperature profiles. You can see temperature depth profiles. The boreholes run from 200 meters depth to 700 meters, here 1200 meters, 600 meters. So, but everywhere you see this upper part, no matter where you are, and I'll show you other continents also. No matter where you are, this upper part shows this curvature. Okay, I'm not used to this pointer. Do I have a stick or something? Okay. Okay. So so this is what you find, and the entire study, this branch of study actually started. The pioneering study in this game was the study by Lackenbach and Marshall, which was published in Science in 1986. That was the first study, and this study is from Alaska. In Alaska, what happens? It's a permafrost area, permanently frozen ground, and there is not much of groundwater movement. You know, if groundwater movement is there, then the temperatures in the subsurface can get perturbed, right? They can go anyway, and therefore you are in trouble if you interpret it wrongly. But here, this was a very safe place. And here, when they measured the temperatures in different boreholes, these measurements were for a very different purpose, to determine the heat flow in the area. So when they measured, they found in almost all the temperature profiles, this same curvature. Okay, this was in Alaska. And this part, the shaded part, as I explained to you a few minutes ago, is the perturbation, right? So the temperature, do I have? So again, basically for the people who have studied from geology background, what I would want you to understand this point, that if you expect temperatures to increase systematically with depth, okay. However, when you actually measure them, what you find is temperatures in more than 500 boreholes, and I can tell you that you will find this. Now, what has happened is, because of the surface temperature change, that temperature change diffuses. If the climate has warmed, then that warming signature will diffuse in the subsurface and perturb this natural temperature field. So this temperature, for example, will move there, this will move there. Okay, so this is the perturbation, this area is what you are interested in. And if you can invert it using different mathematical tools, then you can get back the change of temperature that happened and the time during which that change took place. Okay, so for example, in India, how much is the warming rate? Anybody? Over the last 100 years, how much it has warmed the atmosphere? 3 degree. That's a little too much. No. Right. So it's like how much, Dr. Gandhi? 0.6 to 1, 0.7, 0.6, 0.6, 0.7 degrees Celsius for 100 years. Okay. So if you do this exercise in India, what you should get is, if you do an inversion and find out this, then you should get a warming of 0.6 degrees Celsius over 100 years. Okay. Now you see what happens. So here, what I am showing here is the same thing that I explained to you. So suppose you have a surface, this is surface temperature versus time plot. And I am taking a very simple case. Okay, suppose the temperature. Yeah. Suppose the temperature is at a level T0, for example. Okay, it has been continuing at a level T0, and at a particular time, small T0. Okay, so this is the temperature, surface temperature. Now let's assume that if you measure the same situation in a borehole, this is a borehole, this is the borehole column, these are rock, and at different depths, you keep on measuring the temperatures, right? So if you assume that this is a reference state, and that is represented by this vertical temperature profile. Okay. Okay. Now, if you increase the temperature to capital T1, okay, at a time small t1, that means after some time, this will, as I explained to you, so this will get perturbed because the surface temperature has changed. That will diffuse into the subsurface and it will go on perturbing all the temperatures, and you will get a temperature profile like this. Okay. If you allow some more time to pass, so at time t2, without any further change in surface temperature, what is going to happen? The profile will assume this kind of a shape. Okay. Nature does not like sharp corners, you know. So what it does is, if you just allow time to pass, the diffusion to occur, it will slowly do this, this, this. So this level will remain same, but it's just the time that will go on increasing. So this depth is a measure of the time. So temperature changes propagates downward with time in the earth. Okay. In the real temperature scenario, so if you have at a time t0, you have this, then at a time t0 plus some time at a later time, the temperature profile would look like this, provided there is a warming at the surface. Suppose there is a cooling. Suppose this is a negative temperature change, then you would expect the opposite, right? Then you would expect the opposite. So it's possible. For example, if you go deep in a forest, deep inside a forest, deep forest, there if you measure temperatures in a borehole, the surface has not seen the sun, or roughly, it has not seen the sun. So that will be an artificial cooling at that place. So if you measure temperatures in the borehole in that place, you might see this. So it's not always that it will be increasing, it can also show decreasing. The whole process is governed by one very important parameter, that is the thermal diffusivity of the rock or soil. And that thermal diffusivity ranges for very common purposes. We can use the unit meter squares per year, square meter per year. So typical mean value is about 32 square meter per year. You can also extrapolate it, 32 kilometers square per million year, it's the same. But what happens is, as you go deeper and deeper, the earth is a low pass filter. So it cuts the high frequencies and only preserves a low frequency record, right? So it's a low pass filter. You understand what I mean? So if you see the surface air temperature record, which IITM measures and IMD measures, you will see a lot of fluctuations. That's the high frequency. If you pass the same thing through the earth is a low pass filter. So it will cut down those high frequencies, but it will give you a more smoothened version. Right? It's a low frequency only will be preserved. So, so as you go deeper and deeper, because you are losing the high frequencies, you are also losing the temporal resolution. Temporal, that means time, in terms of time. So as you go deeper and deeper, you are going back in time. The temperature record is going back in time, but you will not be able to very reliably talk about the time as you go further deep. So we have seen that generally up to 200, 300, 400 years, this works quite well. Beyond that, the signal diffuses. Okay, signal becomes more, attenuation also takes place, things like that. So you can go on increasing this to, if you like, extrapolate that, but you will lose the temporal resolution. Ask any questions whenever you want. Okay. Okay. So how do we go about interpreting that? So as I said, so this is the temperature profile which we actually measured. This may be a temperature profile we measured in a small village in Tamil Nadu. Okay. Now this is the temperature profile. This is the steady state temperature profile as you would expect, right? In accordance with the Fourier's law, right? So the geothermal gradient, for example, you would calculate in the linear part of this profile. You would get the geothermal gradient. But in the upper part, what happens is in the top 15 to 20 meters, you have the annual. This is the diurnal and annual variations. So, do you understand these diurnal variations? That is variations throughout in the course of a day, right? So, if you measure in the earth, you will see that the diurnal variations that you see at the surface, they die out by about 50 centimeters to a meter. Okay, within half a meter or 1 meter, the diurnal variations die out, decay to insignificant levels. What about the annual variations? There are annual, seasonal, and annual variations also of surface temperature, right? So if you measure throughout the duration of a year, you will get a curve. Now, studies have shown, and we have seen that those variations die out within about 15 to 20 meters. Okay. So here in the top 15 to 20 meters, you have the effect of the diurnal and annual variations of surface temperature. Below that, in this zone, you have the effect of diffusion of decadal and century scale surface temperature changes. So this is simply the diffusion equation. Okay, so this is temperature, this is time, this is depth, and this is that parameter, thermal diffusivity alpha. Don't go into too much of that right now. But what I mean to say is that this is the zone where you have the diffusion of decadal to century scale surface temperature variations taking place. And therefore, this is the place where we are interested in this class. And below that, you have the Earth's steady state heat flow. Okay. And that is heat flow, as you know, is given by Q is equal to thermal conductivity multiplied by a temperature gradient, geothermal gradient. So any flow is conductivity multiplied by a gradient. So heat flow is thermal conductivity multiplied by gradient. So you compute the gradient here, you measure the thermal properties of the rock in this depth interval, and you can get what's the heat flow in the area. Okay, now how do we analyze this? It's very easy. You don't have to be afraid of mathematics too much. So this is the zone, the stippled area, which we have to isolate first, because we have to interpret that area. Okay, and we can isolate it very simply by removing this steady state gradient, that is T0 plus gradient into depth. So that is y is equal to mx plus c, basically straight line. So you remove that straight line from the observations, and what you get is a reduced temperature profile. So temperature with depth scale is the same, but those are the reduced temperatures. Those are the actual observed temperatures. These are the reduced temperatures. Reduced means only these differences. Okay, and then you can use different models to fit this anomalous signature. Okay, for example, the most commonly, if you don't have any information about that area, you can use a ramp model. Okay, that means the temperature has gradually, systematically increased over a period of time or decreased over a period of time in the past. So if you use the ramp model, and that involves the complementary error function, those who have studied mathematics or physics, they may identify this. And you can fit this, and what you can get out of it is, okay, so much of warming has taken place over the past so many years. Okay, so this entire inversion is parameterized in terms of two parameters. One is the magnitude of the amplitude of the temperature change, and the other is the duration time in years. So at this site, for example, it shows 3.6 degrees Celsius over a period of 74 years. Okay, this is a real example. As is located because of the natural climate change or because of the local conditions, maybe industrialization, maybe local heating. For example, if you take an area where there is a lot of buildings, okay, so there you may see a slightly higher rate of warming and things like that. So, but what I am saying is the method. This I'm showing the method. The method very clearly gives us in the information that there has been so much of warming over the past so many years. Yeah.
Does it also depend on the rock constitution?
Yes.
What the rock
Yes.
is there, the borehole is?
Yes. Yes. It does. It does. So this is an average value. This is an average value. Okay. But different rocks can have slightly different thermal diffusivities. But much more important is the local site conditions. Okay. So, for example, the example this this was if I remember, this was a site where for oil exploration in Alaska, there's a lot of hydrocarbons. In oil exploration, they built a lot of pads, cement pads, concrete pads around. Okay. And in that area, within a short period of time, a lot of surface temperature change took place. And that is what is seen from the analysis. If you see 7.4 degrees over 47 years, 4.8 degree over 74 years. So this is possible. Okay. Otherwise, also, even as you go in the Arctic region, the warming has been the maximum there. So that also is included in this warming.
How did we deduce the number of years in depth?
Yeah.
How did we deduce that? The age. The other slide.
So if you invert this anomaly,
Yeah.
the red ones,
equated with the age. Okay.
Simple diffusion equation, solution of the diffusion equation. Diffusion means time. So that will get depth will get converted into time. We can discuss this much more. you understand this over the last few days in the course we have seen that every method you measure something, you don't measure temperature directly. You measure something which is then calibrated in terms of temperature. Here you are measuring temperature directly. Okay. Then the other advantage is that the earth, I explained the low pass filter action. It filters the high frequency noise and maintains only a running record of the long term mean and departures from it. This is what is climate change, right? Climate change, you would not want, you cannot get from any of these methods what was the temperature on a particular day. On 15th January, what was the temperature? 18th January, what was it? You cannot get that, and you don't need that. That's not climate change. Climate change is the long-term secular variation. Right? So the Earth does that for us. Instead of using a filter, mathematical filter, the Earth is actually behaving like one. But if you look at the air temperature records, they do not have this filtering action. So you have the high frequency signal, which you have to smooth out anyway in order to make a sense for a long-term change. And now this thing I will explain more as we go ahead, that this method has an advantage that it can extend the surface air temperature record back in time by a few hundred years. Okay.
I have a question, sir. So you showed that all the profiles, the curvature which is actually represent the diffusion, so the temperature which radiation in the top is moving in the subsurface. So then those curvature is limited to maybe 200 meters or 50 meters, something. So. Yeah. But I see all of the records are having the depth of 700, 800 or something. Why do
because these boreholes were not drilled to study climate change. Okay. The temperature measurements were made to determine the heat flow of the earth.
Okay, okay. Is already there?
Heat flow of the earth. Okay, from 1930s all over the world, people have in geophysics, one of the most important thing is to measure the temperature of the earth and the heat flow of the earth. Okay, so the earth is cooling and the heat is coming up, and through the surface the heat is lost continuously, and it's measured per unit area per unit time. So for example, typically 50 milliwatts per square meter is being lost on average. Okay,
so what is the longest profile available?
12.6 kilometers. That's only one place in Kola Peninsula in Russia. But these boreholes, now what was done is, if you, for heat flow, this part was of no use, so it was treated as noise. Okay. People looked at this, this systematic, this linear part, this linear part in the temperature profile or the gradient profile to compute the gradient, and then multiplied by the thermal conductivity to measure heat flow, to determine heat flow. So this part was always treated as noise. When I started my research career, basically, this part was treated as noise. And that 1986 paper by Lackenbruck and Marshall overnight changed that noise into a signal. Signal for climate change. Okay, so I'll show you some examples from India. Come on. Now, if you look at the distribution of boreholes that have been used for determining climate change in the northern hemisphere, you can see this is the latitude range. Okay, and you can see the distribution of boreholes that have been used in different latitudes. What India does is to fill up a very important low latitude gap. There was a low latitude gap in such studies, and India, being in the latitude band of about 8 to 28, 30 degrees north, very nicely fills up this gap. So what we did was, these are all the boreholes that have been measured for heat flow purposes, starting from 1960s. And we took all these temperature profiles. I started, it was part of my thesis, PhD thesis also. And then we looked at, so these are the different temperature profiles in different areas. So interior peninsula, east coast provinces. These provinces are named here in terms of climatic provinces as given by Hingane and his colleagues, 1985. So, so you see these temperature profiles in different, this is in the Rajasthan area, this is Kerala, this is Andhra Pradesh, this is these are Ahmednagar profiles, these are Pune profiles. So during my thesis, I used to go and measure temperature profiles in all different regions. Pune, Ahmednagar, these are, I think, in Kurnool, in Anantapur district, in Andhra Pradesh at that time. So these are Bangalore, these are Tamil Nadu, these are in Rajasthan, in deep mines we measured. Okay, and everywhere you see that the upper part has some signal here in terms of climate, and this we started looking at. Now you see this. So we started fitting the geothermal gradient, the linear part, and we could see that these are the anomalous parts. And then we started fitting them with different models. And typical sample ramp fits I'm showing here, many of them actually fit very beautifully. Although it's all mathematics, but it fits really beautifully. But then you also have to be aware, you have to be cautious. If you see some such nice fits, you tend to think that, okay, only this is the reason for the curvature. You have to be careful about the other different causes of curvature that are possible, as I told you before. But in general, it's really a promising thing, promising result, as you can see. These are in Hassan, Pavgada, all these areas in Karnataka. Okay, so you have seen many. Now, what else is possible? As I told you, you are also able to determine the land use change that has taken place in the last few years or few tens of years. Okay. So those we were able to find from some of those temperature profiles that there is a warming in general, but on top of that warming, there is a cooling signal. Okay. Why that can happen? Any guesses? I don't know why they have happened, but do you have any guesses why that could happen? Or how that could happen?
Location, is it?
See, these are the invert any location. This is Ahmednagar, these are Ahmednagar, but you have to go into that particular site to know what are the local conditions. These are Ahmednagar profiles. These are Pune profiles. This is Latur, Hilari. This is Bangalore. Bangalore always gives a very small signal, but a very depth-wise it is the highest. But you see, what I want to point out is that they show this part of the profiles. They show 1.460, 1.680 years, 1.8. On top of that, you have some very recent effect. Very recent effect over the last few years, basically. Okay.
More rainfall events, extreme rainfall ones.
Could be, but few years, I'm saying. Okay.
Yeah, it can happen.
So one thing, for example, could happen. Agriculture, irrigation, lot of irrigation.
Maybe new dams nearby.
Yeah, but irrigation is a very big factor, sir.
Increase in the sugarcane production
Possible.
because some grants.
Because they need a lot of water. Possible. And if your borehole is in such a field where is located in such a field, these boreholes are for different purposes. People use them for different purposes. But if it's one is in such a field, then it is possible, because suppose there was no sugarcane cultivation earlier, and it was part of the natural, the normal scenario, and suddenly over the last 10, 15, 20 years, there has been a lot of sugarcane cultivation that has started. It is possible. It's possible. So on top of a warming signal, there is a cooling signal. Okay, so this is also possible to resolve using this method. Point I wanted to mention here is this. Now, if we take South India, 8 to 20 degree latitude band, if we take all the reduced temperature, here there are about, I think, 75 temperature profiles may be there. And we converted them into reduced temperature profiles by removing the steady state part. And if you look, there are some which show cooling, of course, because of local microclimate issues. But 90% or more show that warming. Okay, and if we took this entire thing and inverted as a cluster, you can get numbers like 0.9 degrees Celsius over the last 127 years. So you can say 1 degree over the last 150 years.
More than the atmospheric?
More than, slightly more than that. But this is the average of many things. Okay. This is average. See, if you want to look at that, then you have to really sit down, and what here I'm showing is demonstrating the method, basically. So here you see the change in temperature. So if you take 0.9 plus minus 0.3, so it could be 0.6 also.
It is same.
Yeah, and the median, the time duration is about 150 years. Time is less well constrained than the amplitude of the temperature change. Now, if you look at the global database, so you can see the distribution of boreholes by latitude, and even India is included here. If you take that, then you get about 0.8 degrees Celsius centered around 1850s, mid 1800s. Okay, don't worry about 1840 or 1830, don't worry too much. Mid 1800s, 0.8 degrees. Since mid 1800s, there has been a 0.8 degree increase in surface temperature on average throughout the world. At some places, there may have been a cooling also. At some places, it may be 0.1 degrees. In some places, there may be 3 degrees. In Arctic region, you can expect 2 degrees, 3 degrees, 2.5 degrees. But on average, this is what you get. Okay, I have some time left.
Yeah, 10 minutes.
Okay, so maybe I will cover one other thing. I will not cover but is this interesting to all of you?
It's very interesting. It's very.
So just now, we also found, and researchers all over the world, they have found that it is possible to combine the geothermal record with the meteorological records. Meteorological records of surface temperature you have seen are produced by IMD, IITM, right? And all over the world you get, okay? So on land and sea, now it's possible to combine the information that you have in that record, which is short, 100, 120 years, maybe, with the geothermal record, which has a slightly longer reach. Okay. So we considered the red ones are the borehole sites, as I showed before, and the meteorological stations that we took from the IMD dataset are shown in blue triangles. Okay, we selected meteorological stations which are near our borehole stations. Okay, there is no point taking there where we don't have boreholes. We can't compare or combine information. Now the division is, the classical division of climatic provinces, broad division of climatic provinces: interior peninsula, west coast, east coast, north central province, northwest and northeast. If you look at the average surface air temperature records in each of these provinces, forget about the red line, don't worry too much, but you see these staircase plots. Okay, so these are the kind of average that you get. Now, how will you combine? Because this record has a lot of high frequency component, right? And the boron record doesn't have this high frequency component, right? So how will you combine them? How can you compare them? You can compare apples with apples. You can't compare apples with oranges, right? So what you have to do is you have to bring both of them at a common platform, right? So there are ways to do that. One is you can take the surface air temperature plot, pass it through the Earth's filter, drive it inside the ground, okay, method, and by using the properties of the Earth, and convert it into a synthetic borehole temperature profile, temperature depth profile. Okay, you have your borehole temperature depth profile. Now you are converting the surface air temperature with time plot into a temperature versus depth plot, right? And then you can combine the information. Okay, but what happens is, suppose this is the temperature surface air temperature record, and at so this, what is one of the most common ways of doing it is to break up into n number of events. Okay, so n number of temperature differences. So T1 minus T2, T2 minus T3, T3 minus T4, each are for years, different years. Okay, but what happens for the first one? For the first one, you don't know what was before. So you suppose this is T1, you don't know what was T0, right? So you assume that it was, we call it a pre-observational mean. Just name it, a pre-observational mean. Okay. So we assume that before the start of the first temperature record, there was a pre-observational mean, some temperature X or PON, whatever. And then you go on converting this into a temperature versus depth plot. Okay, so you see here what is done. What we have done here is we have taken different choices for the PON. Here I have shown only 3, but we can take a different choice. So you can do a full calculation. You can vary POM from using different iteration schemes, inversion methods, iteration schemes. You can do that, and you can come up with different subsurface temperature profiles, synthetic temperature profiles in the subsurface. Okay, and out of these, the one which best fits your borehole temperature profile will be the best choice of a pre-observational mean, right? So with that, you are able to get, for example, for South India, we see that the open circles is 0.6 degrees lower than the 1961 to 1990 mean. So meteorologists often use this 1961 to 1990 mean, 1971 to 2000 mean, things like that. Okay, so this is that 1961 to 1990 mean, and the POM, that pre-observational mean that best fits this is minus 0.6. That means 0.6 degrees lower than the 1961 to 1990 mean. That means you have some control over what was before. Okay, you don't have high frequency. You cannot reconstruct a high frequency signature before like this, but you get some kind of a long-term average. Okay, there are ways to determine how much farther back in time you can actually use that long temperature average. I'm not going into those details now, but what I'm saying is it is possible to get a long-term average before the start of the meteorological records. Why this is important? Simple terms. you can say that, okay, in the 18th or 19th centuries, in the 19th century, for example. Why 19th century? Because with the kind of data that we have in India, the geothermal data, we cannot extrapolate it like 400, 500 years or beyond. Okay, so those details I'm not going into, but let's say from the 19th century reference, the temperature today has increased by 0.6 degrees with respect to the 1961 to 1990. So is this information more valuable than what we used to get only with the geothermal record? Certainly. Now we have a baseline, 19th century baseline temperature. Okay. And then you can use many other parameterization schemes. Mathematically, you can do a lot. And you can, it is possible to, instead of one single average temperature extending back to 300 years or 200 years, what you can do is you can use different parameterization schemes and you can get somewhat more information for the pre-observational period. So I will not go into that, but I'll show you some curves. Now, if you look at this pre-observational mean, if you look at the misfit diagram, you can see very clearly that the estimate of pre-observational mean that we have got is quite robust. The misfit, the 0.6 minus 0.6, it has a very clear low RMS error, right? So it's a robust number. If we did this for the entire India, but for other parts of India, we don't have much data, but we got an average of minus 0.8, which is not very reliable, but this is very good. 0.6 is very good because we have a lot of data. And so, in summary, you can say that, okay, you have this 1961 to 1990 mean. So if you look at the whole thing in terms of a temperature versus time history, so you have the 1961 to 1990 mean, you have the surface air temperature record that comes from the meteorological data combined. Then you have 1995 to 2005. This we use because the study was done in 2010, so we took that part of the data. So this is valid for that time. We are 10 years ahead now, but it doesn't matter. See, this is the level, and then the baseline POM is minus 0.6 degrees lower than the 1961 to 1990 mean. So if you take from that baseline up to 2005 or 2010, you already have a clear additional 0.35 degrees Celsius warming. Okay. So this is what comes out of combining the two information, the meteorological as well as the movement record. Okay, I'll probably not go into all this, but I'll just show. I mean, many of you must have seen this in the last few days. I was not here, but there are different multi-proxy reconstructions that have been suggested or proposed by different people in the world. Some are, many of these reconstructions take a lot of data. For example, you would say Brifa or Esper et al. Those are very, very dense tree ring records covering a large part of the world where, mainly Europe, and where such data are available. So, for example, tree rings, if you take, Dr. Bhavlakar was explaining to me the other day on Monday that in the for the Himalaya, you get very good record in terms of temperature, but not so in case of central. I mean, he's the expert, he will tell you more. This part is more dominated by the monsoon. So there are problems with every data set. Therefore, what is done is use multi-proxy reconstructions. So multiple proxies you combine and then come up with different. So starting from about 1500, the instrumental record is only here. We need to know the past. And why we need to know the past, you have already studied in this video. I'm not going into that. But to know the past, you can use different different, for example, Mike Mann, it has also a lot of problems. But the point here is that he combined all the different proxy information. Combining all the different proxies is not a straightforward job. So that also has its uncertainties. So you have to live with uncertainties in this game when you do paleoclimate reconstructions. Okay. How does the borehole temperature feel? So the borehole temperature, I showed you a very simple case. You can use singular value decomposition and other tools, and you can go further back. You can. Some people in Europe have also, and Canada have also been able to infer the last glaciation, okay, event in the from the borehole temperature curve. Even the Germany, that KTB borehole, 9-kilometer deep KTB borehole. So people have very good workers have actually inverted that temperature profile and got information about much further back in time than what I am talking about. So you have the multi-proxies, and then you have the temperature. This is the hybrid model that I showed period 1. So it really compares quite well. And well, as Dr. Sushma was saying on the first day, her method is excellent, is the best. I would say, okay, this method is the best, and you can debate. You can debate. Okay. And then there are different IPCC scenarios. Probably I'll not go into that because I have already overshot the time. But what I mean to say is that this method is a very good method which can add value, maybe complementary value to other reconstructions that you have studied in this week. Thank you very much.
Questions?
Yeah.
Introduce yourself.
Borehole activity in the Himalayas, like you saw borehole sites mostly located in the southern region of India. Why didn't no boreholes at the Himalayas?
Boreholes are usually not drilled for research purposes because they are quite expensive. Boreholes are drilled for what? For oil exploration, for groundwater exploration, for mineral exploration, for cultivation. Okay. Now, in the Himalayas, many parts, there is no oil exploration going on. There is no, maybe in some areas there are groundwater exploration, but then in those areas, if you go, you might find some boreholes. Mineral exploration also is almost not there. On top of this, if you go to high Himalaya, where the altitudes are like Leh is 3.6 kilometers above mean sea level. In those at those altitudes, humans themselves get fatigued very fast. Similar case is with the machines. The drilling machines also get fatigued. So it's very difficult to drill with such conditions where you have low oxygen. Right? So there are many reasons why there are very few boreholes. But if you go to some areas, you will still get some. Maybe we are not gone.
So one more. So while drilling the borehole, the machine that will bore, and while boring there will be some temperature heat generation while doing
Friction.
due to friction. So how do you account for those temperatures?
That friction is a very transient phenomenon. Okay, that friction, and there are other things also similar, other perturbations also which happen during drilling. So what is done is once the borehole is drilled, you leave it for about 48 to 72 hours. You don't disturb it. So many of these perturbations, they are gone by that time. So this we did with our experience. We did measurements at different times, after the drilling, and we found that after 48 to 72 hours, these perturbations, 95% is gone. Okay. But in the case of oil wells, we will not get such beautiful profiles. In the case of oil wells, also there are other problems. There is a lot of mud circulation happening. And because of that mud circulation, we will not get a steady equilibrium condition in 2 to 3 days. It may take 1 year. Nobody will wait in the borehole for 1 year. They will drill and go. They will close the borehole and go. So for scientists, there is nothing there.
Sir?
Yeah.
Sir?
Yeah.
Sir, I'm from NCS MOS. No, sir.
Very
Sir, I'm
nice.
Vaishali from NCS.
Yes, you are Vaishali, I know. Yeah.
Sir, we have board in Northwestern Himalaya, the MPG project which is going on.
Which project?
MPG, multi-parametric geophysical observatory is
good
there
too.
in Guttu.
Good.
Yes,
Yeah.
sir, there we are having two boreholes.
Okay.
But that is being used for the radon measurement.
Okay.
And
How deep are they?
65 meters.
That's too shallow.
Too shallow, but that probe is situated at just 20 meter depth because we are using that for the radon measurement. So these type of studies can be carried out, or what is the
This type of, not exactly this type of study, but something different. You can talk with me sometime. I mean, what we did was we set up a observatory like this at one place to study some fundamental processes in this method. So there we have been measuring at temperatures at depth of like 20 meters. I'll show you some. For example, if you have a 20-meter board and you go on measuring the temperatures in different seasons throughout the course of a year, you will get a lot of differences in the top 15 meters or so. Below that, so this I wanted to use to show that seasonal and annual variations, they die out by about 15 to 20 meters. So you see by about 14-15 meters, this kind of variations die out and you get. So this kind of experiments you can surely do in that borehole. You can also do some other things. For example, now geothermal heat pumps are coming up, where you need to know what's the temperature, at what depth the temperature doesn't change throughout the year. That's a very important thing. So it's a similar application. Okay. So this kind of things you can do, but we can talk about that later on. I don't want to eat into this time.
Good morning, sir.
Yeah.
My name is Yashodhara Gandhi. My question was, can we tell the possible climatic process which affected the temperature from the borehole temperature data, or we need other proxies?
The processes.
Yes, sir.
No, the processes. See, this is from this for processes we need to know what's the land use history of that area. Those are some of that is available with the district administration in many cases. Like, okay, when did the major afforestation start, or when did the big building construction start? So this kind of when did this irrigation, for example, you mentioned about the sugarcane irrigation. So or irrigation in general, agriculture. So maybe 100 years ago in that area there was nothing, but maybe 40 years ago a lot of irrigation activity started. So this is a good land use change information that you can use to interpret these problems.
Another question, sir. So, like you mentioned, it's more like pass not failure. So, how far we can go? Like,
yeah. So it depends on how deep your curvature is. In India, we have seen that the curvature doesn't go below 250, 200, 250 meters. In such cases, you really cannot go beyond maybe 350 to 400 years. But in some cases, for example, in the higher latitudes in Europe and in North America, people have been able to go even further back, up to 500 years, 600 years.
and
But
so,
don't go beyond that, because as you go deeper and deeper, the time resolution goes.
thank you, sir.
Just want to ask about one thing. Like we were measuring the temperature on the wall of the borehole.
Yes.
So is it like the diffusion of the air that happens?
Excellent question. See, when you want to measure inside the earth, okay, you can ask. I mean, your question is like for others. In the borehole, there is always a water column, right? More often than not, there's a water. We are actually measuring in the water column, not in the air. In the air, these the sensors will fluctuate a lot because of convection also is there. So you usually need a good stable medium to measure the temperatures. Now you can ask the question, okay, you are measuring in a borehole column which is full of water, but you are saying that these temperatures are the earth temperatures. Why? This is probably rephrasing your question, right? Can you answer, anybody? I already gave some hints before. Why do you wait for 48 to 72 hours? So that's in addition to those issues, also the water column temperature, which is surrounded by an ocean of rock, infinite Earth medium, right? So if you look into thermal inertia, thermal mass, so you will see that this borehole water column is a very small water column compared to the surrounding rock formation, and therefore within a certain time, which is like maybe 1 day, 2 days, the water column temperature comes in equilibrium with the surrounding rock formation temperature, and therefore what you measure in the water column are actually the rock.
So thanks to Professor Sukanta, right? He really learned a new technique. Maybe actually not many people. I hope that many people here would know about this technique. And actually, because I was also discussing, this is really a new insight, and it is really complement. So what is happening inside the Earth surface? So I thank Professor Sukanta.
Thank you. It has been a pleasure sharing with you something which I did long ago, but something which I have interest to do in future as well.
So some youngsters should come up and take it forward. So now, we have actually they are from here. So it is my pleasure to invite. He is my senior and my guru in dendro work. Is Dr. Hemant Borgaonkar, and he has done a lot of more than 35 years or work on this field. And the people who has little knowledge about the treating, they must have read his paper somewhere or other. So he has plenty of papers and extensive work in Himalayas, Kerala. For teak, he is very famous. Most of the works are done in teak, done by him. So he will. You already have the tree laboratory visit. So he will talk about basic sampling techniques and what are the statistical things which we use and how we generate the tree records. So I welcome Dr. Hemant Borgaonkar.
Good morning. Good morning, all of you. Now, the title of my presentation is Climatology, Understanding Past Climate from Tree. Now, during last 3 days, we have learned a lot of proxies, different techniques, procedures, and how to reconstruct or how to get information about the past climate. Now, today I am going to give some information about the high resolved proxy, that is tree. Tree ring or dendro. The dendro is the Greek word for wooden log or wood. In chronology is the time series. Dendrochronology. And if you learn dendrochronological technique, then you can use data to variety of applications like climate, dendroclimatology, ecology, or hydrology. So you can have big scope. What is the advantage of using tree ring? Tree rings are annually resolved. Calendar year can be assigned to each ring, and very precisely we can get rings. There is no doubt of any doubt. Show continuous record and three widespread distribution. This is very good advantage. But only disadvantage is we can go up to 1,000 years very easily, 2,000 hardly, and beyond 2,000 very rarely. If we define the dendroclimatology, it is the science of reconstructing past climate by using clearing, is known as dendroclimatology, which is a part of paleoclimate setup, deals with variations on interannual to century scale. The study is based on tree growth and climate relationship and involves modeling of the relations between climate parameters and various characteristics like weight, density, and isotopic ratios of annual rains formed by certain climate sensitive trees. These models are used to reconstruct past climate by means of clearing chronology of old trees of age of hundreds of years. That is the dendroclimatology. If you see the history, then there is a mention of clearing back to 322 BC. Herostratus, he wrote about 9 volumes of history of plants, and he mentioned that the 2 conifer species have clearing structure. Then all these other scientists, they have just mentioned about the clearing and counting of the rings and age of the tree. But there is no systematic procedure developed since A. Douglas in Arizona. He initiated this study. He is known as the father of dendrochronology. Andrew Douglas is regarded as the father of dendrochronology. Douglas was a student of famous astronomer Pewell Loyal, who in 1894 sent Douglas across the country to build an observatory in Arizona. While acquiring a timber for observatory's construction, Douglas noticed similar rings with pattern in stumps of the trees cut for constructions. By the early 1920s, Douglas had pioneered the science of dendrochronology, most importantly, the principle of cross-dating, which he applied at various variety of different disciplines from climatology to astronomy to archaeology. And this principle of cross-dating is equally useful in today's climate histories. And he established the laboratory of clearing research at Arizona. And this is the biggest and old laboratory having good good clearing collections all over the world. These 2 scientists, they are known as the father of European dendrochronology. Bruno Haber from Germany began using Douglas techniques to initiate clearing research in Europe, and today is considered the father of European dendrochronology. He and Douglas were good friends who were published many articles over 30 years of period and firmly established the usefulness of this field to European tree species. Fish Wang, he has several hundreds publications and he trained hundreds of scientists all over the world. He is credited with introducing clearing technique to ecological application and was instrumental in showing how clearing can be used to analyze environments previously altered by humans. H.C. Fritz, Harold Fritz, he is the father of modern dendrochronology, and he started to use computer in the dendroclimatological studies. And Malcolm Hughes. He's the former director of hearing laboratory at Tucson. And he also have good work over the Russian region, European region, as well as America. And he reconstructed a lot of parameters for climate. Tom Sweetnam, he is also former director of Laboratory of Peering Research to Solve. And he has developed very long forest fire history from peering records of giant Chicoria forest of Sierra Nevada, California. Edward Cook from Columbia University. He introduced the variety of computer techniques and method of standardization, variety of options he developed, and he developed a program, ASTEN, which is auto-regulation standardization for peering research. Dr. J. People is a former director of IITM, and he is a pioneer of Indian dendro criminology. He initiated 2 classic papers in Mosam, suggested that the trees of Himalayan zone are most appropriate for dendroclimatic research with well-defined growth rates, which generally display a very prominent response to temperature. As a primary survey, few species of subalpine temperate, subtropical and tropical response of Himalayan zones have been identified by Dr. Pine. These 2 papers were the guiding source for the beginners in the dendro research. These are the Indian species useful for dendroclimatic studies. From Western Himalaya and Eastern Himalaya, most of the conifers are there. And from tropical region, teak is very potential species for monsoon reconstruction. These are the different characteristics of peering which can be used for the dendroclimatic studies, varying with there is early width, acute width, total ring width, ring density, early wood density, late wood density, total ring density, and stable isotope ratios in peering scenarios. And that is delta D, delta O, delta C. These parameters can be used for reconstruction of corresponding planets. The cross section shows the growth in pattern, relief wood, late wood. Relief wood and late wood combinedly forms a one ring, real ring. And this is relief wood, late wood. The steps in dendroclimatology. If you want to reconstruct climate from peering, we have to follow these steps. First is site selection, peering data collection, sample preparation in the laboratory, cross matching and dating of individual samples, ring width measurement, determining peering measurements series, standardization. Acquiring meteorological data, temperature, rainfall, pressure, etc. And model tree-growth climate relationship, that is called response function analysis. And reconstruction of past climate, transfer function. Now, site selection. This is very important. The site should be very sensitive and natural. This should be in natural environment. They should not be. They should not have a permanent water source. This is the Himalayan side from Karcha Gangotri. And these are the cedrus deodara trees, height around 30 to 100 meters. And this site is this goes to Gomu, and this site is back of this mountain. And we have collected a lot of samples from this site. And most of the samples are very old, about 300 years. This is another potential site of cedrus. It is from Malari. It is 60 kilometers north from Doshimat. And all these trees, they are stunted, not very big, but they are very old. This is 225 years old. Because of very adverse condition, they grow, and their rate of growth is very slow. This is another site which is near to tree line and glacier boundary. These samples are also very potential for this study. And this is the last tree near the Kailash Glacier Karpa. This is Abyss, and we got the age of this is 510. This is also one site from the Himalayan region. This is now how we collect the sample. This is very risky to stand such a slope. But the information what we get is very important. Now, from Central India and South India, we have collected a lot of samples. This is the Tokaura forest, Chhattisgarh. These are called the Ram, Lakshman, Bharat, and Shatrugna. There are many trees like this, and they don't allow to take a sample from these because they are preserved very big. But the same site trees are available in nearby forest. This is another giant peak from Kerala, Soyapur. And this is, they claim that this is the biggest in Asia. The breast height is 7.2 meters. And this is also preserved forest. And there are also some trees of similar size. So we have collected from this end both the sites. So this is another giant peak from Kerala. Most of you may be knowing this Kandimara is the sacred place, and here there is a boat. Can you find it of my age? Yes, we can find out, but they would allow to touch this. Okay, then sample collection. Now you might have seen this in the reading the paper lab. This is Bora. And Bora has two parts. You know that. And this is the only instrument which we can take the samples of tree. And how to prepare this feeding samples? They are taken to the lab, and they are mounted on the mount. Then they are polished to desired smoothness, and they are numbered. Then measuring liquids. You know this, you have seen this. In while measurement, you have to take the perpendicular distance from one ring to the other. The technique of cross dating. Cross dating is very important and very primary in this whole process. If your cross dating is perfect, then your dating is perfect and your further analysis will be easy. What is the cross dating? It is building a composite chronology with samples is possible if cross dating between all samples is significantly strong. That is, in simple way, the similar pattern of the among the samples. We have to match those sample pattern, and particularly narrowness of the tree, it should be matched among the samples.
This cross dating is done between two trees or between two coasts from the same tree?
All whatever samples we have, all the samples we have to count
From one particular area.
from one source. Because within the tree there is a, generally we take two samples from the tree. Within the tree there is a release. Yes.
So you do this cross dating from the samples taken on the same tree or samples taken from all trees in the tree?
Because we have to get each
First of
sample.
all, we do cross dating within tree, then between tree, then among all.
There are methods how you go. Why does cross dating work? Because trees within the regions will be responding similarly to the overall climate regime in which they grow. Because if, for example, in Himalayan region, middle altitude conifers, they have 1921, 1951, 1892. These are narrow ranges, most of the ranges. Because the monsoon climate is very dry and warm. So that produces the moisture test condition over the major region over there. So those are the point areas. So we can use those years to help the
Like we call index bands, let's say index bands.
cross dating has two techniques. One is skeleton cross. Skeleton cross is just whatever your observation about the sample should be reflected on the graph paper. Each line, vertical line of graph paper corresponds to one line. And you plot. Again, the narrowing is the longest line. If very broad ring, just try to be. But all observation, whatever you feel about the sample, you display on this graph paper. This such graph papers are prepared for all the samples, and then they are cross-matched. Then alignment of plots. This is favored in European people, they use this. Regarding cross-dating, you must start memorizing which rings are particularly narrow or which have noteworthy properties such as very wide ring, very narrow ring, cross ring, thin latewood ring, thick latewood ring, right ring, ring with raising ducts, false ring. Such observation you should memorize, and then it should be reflected on the graph paper. And this is very time-consuming job. But once it is done very well, then further analysis is smooth. You see, this the widest ring is connected. It is green line. Green line is the widest ring. You have written broad. In the red line which points to the ring of average width, but it seems narrow compared to the proceeding rings. Now see this ring. This is not very narrow, but compared to adjacent ring, it is narrow. So it is average ring. So put small bar. And the narrowest ring are connected to blue lines. Is the longest way in this creating problem. So these are the narrow ring. This is the narrow ring, and we put the long bar. Similarly, we prepared for each samples. Now these are the 3 samples. Square and drop. And this is the average of this. In the common features, they now see this, they are narrowing, this narrowing, this narrowing. Now in master chronology, this will be narrowing. Now such if pattern is 80% similar patterns are observed in all the samples, then they are prepared from there, they prepare the master chronology and then dating is performed. So how date is given? The last trade is the latest trade. And near to bar, the we know the picking year or sampling year. If last ring is complete, then you can put that year in the last ring. If it is not complete, it generally season start, growing season start by March. And if you collect samples in May, June, the last ring is not totally formed. So you leave that in and put earlier year to be full complete.
Excuse me. What is a false ring?
False ring is the ring type structure. We will feel that it is the ring wanted. It is not actually removed because of some momentary changes in climate exchange. For 10-15 days, climate is very extreme. Then we go stops momentarily. The same size is small. So we feel that it is being actually, it is not actually. And it can be observed in the microscope, and that false ring can be corrected in this cross-matching process.
But how do you identify that it's a false one? How do you discriminate between a false ring and a real?
Yeah. Now, in cross-match doubts, if all these portions, narrow rings are matching, and in some proportion they are not matching, they are just one ring off, one ring off. If we put that in, then it is matched. So we see again the sample if there is any missing ring. Alright. And missing ring is also observed through microscope. It is identified. You see, these are the some common pattern in these samples. 1793 white ring with label. You see, these are all these are data samples. Now, narrowing of 1806. 1860 with without a summer white ring. and white rings, they are also mentioning this. So such common pattern, if we find among the samples for more than some 70 to 80%, then we can say that it is cross matched, and we can date samples accordingly. No standardization. This is also one another important aspect of hearing analysis. Climate is not only influenced with the wet year, dry year, young rain. But climate is not the only parameters which influence on the rain. There are other parameters like soil, slope, water table, so ecological parameters like competition among the trees, injury, insects, fire, and all these parameters. Impact of these parameters, the width is formed. Now, ring width, major ring width, that is RP, is a function of C, D, D, and E. What is C? C is microclimatic signal. D is a biological group. D is tree disturbance signal, like competition, trees, fires, pests, and insect invasion. And E is the random growth signal unique to each species. Now, our interest is in climate, so we have to remove or minimize effect of B, D, C, and we have to try the maximize the signal from climate. This is called the standardization. How the standardization is done? The fitting of growth curve. Like the negative exponential, cubic spline, then polynomial, those curves are fitted, and then index is calculated, and this random growth signal unique to the each specimen is minimized by averaging cross-match chronology of several samples of the same species from a single sample. Now, these are the different curves of samples. Now, this is the exponential. Now, we can fit such type of curves to retrain the train. A straight line can be either horizontal or upward reading. This is the one way of standardization. It depends on the how your sample is downtrending. Then straight line. In most of the cases, they show the negative exponential because of the biological effect. The growth rate in early stage of growth is very fast, and then it is reduces, growth rate is reduces exponentially. That is called biological effect in the removed by negative exponential. This is another example of. Then sometimes polynomials or smoothing splines are also useful for smoothing the splines. Okay. Now this is the example of retraining, and this is the we have often the indexing. Once we are able to get a line to our training scene, we will then have an equation. We can use that equation to generate predicted value of T group for each year via regression analysis. It is very simple. For example, X value, the age of the tree or year, we can generate a predicted Y value. These are the actual values, and these are predicted values. And for each year, we now have an actual value measuring with predicted value from curve D. And we can get index by A divided by B, that is actual value divided by predicted value. Now this is the curve. We have fixed this curve, and this is the index value. This is another type of hearing curve, and we have fit the negative exponential, and this is the index value. Now all series have a mean 1. All series have transferred to the dimensionless index value. All series can be averaged together by year to year to develop a master grading index chronology for size. Now remember that this master chronology now represent the average growth condition per year for all the major series. There is master chronology represent the variation of tree growth of the site. So this is index series 1, 2, 3, and just averaging is from a master property. And for actually our purpose, we collect from one side, we collect about 30 to 50 samples. So all 50 samples, we prepare index series and we average it here. And one series is formed, that is called master chronology. If I say this is the Gangotri tree chronology, it means it contains at least 30 to 50 samples. Okay, this is another way of. Now some statistics are very important. This is a very simple statistics, but this gives the potential of site, the endokinetic potential of site. That is mean variance of the correlation. That is persistence intensity, mean sensitivity, how sensitive your site is. The mean correlation coefficient, that is the variance of the site. Signal to rise ratio and express population signal, that is subsample group. So here these are the index chronology. So this express population signal is very important for reconstruction purpose. If the value is 0.85, that is the threshold of the EPS, and we cannot generally it is accepted that up to EPS 0.85 we can go back for reconstruction. So these are the index series of many samples. And this is master chronology prepared from this. So this is EPS 1. All samples are included. If we go further and we calculate EPS, it is 0.85. Okay, up to this we can go for reconstruction. And for this 0.7, the clearing chronology with less sample, we cannot go for reconstruction. This is a clearing index chronology from the Gangotri region. And these are the 4 chronologies from Gangotri region, and these are the different statistics. All statistics are showing very good potential of the site, and this can be used for reconstruction purpose. the reconstruction of past climate. Master chronology, and we have observed data, climate data about 100 years or so. And then we just go for the relationship between tree growth and climatic parameters, different climatic parameters of the observed period. For this purpose, we use the response function analysis, and this gives the what type of climate, exactly what type of climate is responsive for tree growth. And if it is significantly responding, if it is significant, then same parameter we can reconstruct using the earlier part of the tree. This is response function analysis. Then transfer function analysis is reconstruction of the climate. Tree growth is response function analysis. It uses the stepwise irrigation analysis, where tree growth is predicted and climatic parameters are the predictors. Monthly and seasonal parameters generally we use. Which climate variables can be analyzed from tree because precipitation, monthly or seasonal, temperature, monthly or seasonal, then common drought severity index, El Nino southern oscillations, drought history. Such information we get from the period for about 1,000 years. Now, this is the response, how it looks like. This is the response function of two sides. This is Putti and this is Sangha. This is temperature response, rainfall response. This standardized index, and these are the monthly parameters from previous October to current October. Why we use previous October to current October is this is the end of the last year's growth to the end of the current year growth of tree. Here, the error bars, they show the significant level. If they are not crossing the zero value, then it is the significant response. Here you can see that the winter temperature is more significant on both the sides. This is another two samples from the sites from the Himalayan region, Jangala and Popa. And here also we can see that the winter temperature, because they are very high altitude here in glacier sites, the winter temperature is showing positive response. But in rainfall, we don't find any similar pattern of the response. If we see the overall average response of the Himachal Pradesh or the Gangotri side, you can see the all sides they show the positive response of the winter temperature. Similarly for the Gangotri side. And these are the Kashmir, these are the response of the Kashmir side, Himachal or Uttarakhand middle altitude, and this is Himachal and Uttarakhand high altitude. So in the middle altitude for Himachal and Uttarakhand, we see the temperature and precipitation of pre-monsoon. They show the significant response. While in Kashmir region, little shift is there in the response. The May to September temperature and May to September rainfall, they show the response. In Himalaya, in a high altitude near glacier chronology, the winter temperature shows very significant positive response for all the chronologies. But in other seasons, there is no very significant pattern. Now, why Kashmir and Himachal, they show the different response. The Kashmir climatology and Himachal climatology is different. Now here, the condition of climate is dry and hot in June to September. While in Himachal here, the dry and hot warm season in May, March, April, May, that corresponds to the early part of the chronology. This is the example of the reconstruction of the winter temperature. We calibrate with different periods and we see the different statistical tests. Then same calibrated parameter is verified with the independent set of climate. And all this calibration period, we found that this period is significant. All are significant, but this particular period is most significant. These are the different states of statistical tests of calibration and verification. And these are all given in the notes I am going to give you. And this is the final reconstruction of winter temperature. And the same temperature parameter is also reconstructed by Pune. And you can see that both parameters, both the variations are nearly same. Only there is some leak, this is cooling, and this cooling is due to the temper eruption in Indonesia. What he suggested. But this impact is not significant over the Himalayan region. This is up to Nepal. In even Sikkim and Bhutan chronology, you can see this cooling, but you don't see this cooling in the Himalayan, Western Himalayan.
Sir, does we find this cooling in the peak?
No. Our peak is mainly moisture phase.
The temperature में इतना sensitive है, moisture के लिए ज़्यादा sensitive.
So this is the peering network of India, and we have. I am going to show you some reconstructions from Himalayan region. Yes, I will go first. This is from Western Himalaya. We have noted some dry years and warm years. This is the Millennium Western Himalayan chronology. This is developed by Yadav from DSIT. This is, and he also demonstrated some increasing warming trend after say the 1950s. This is from Himalayan region. You get some warm epochs and cool epochs. And during last few decades, we see the warming. Then this is from Sikkim. And this is the reconstruction of July to September temperature. And here you can see cooling impact of the eruption, two eruptions, Tambora and then Krakatau. And same information is also shown by this different reconstruction. This is from Sikkim, East Asia, Bhutan, and Nepal. So this is one major activity of pages. They have used multi-proxies from the globe, and continental-wise they have reconstructed temperature for 2000 years back. And over the Asian region, totally based on the tree. Totally based on the tree. And IITM data is also involved in this analysis. And this is the Asia temperature reconstruction for 2000 years based on the tree. And this is from Kerala. Here we could get the drought history of 100 years, monsoon drought history of 100 years from peak to peak. And these are the program Dendo software widely used, DPL, Popecha, Arstek. This is DPL have. DPL is the dendroclimatology program library. They have variety of softwares available in this. Popecha, this is the quality control of measurement. This is also widely used. And this is Arstek. This is the auto-reduced standardization. Variety of options are available in this with graphics option. This is a very useful program. Okay. This is the global network of trading. And these are the sub-fields of the dendrochronology. And in India, the dendroecology, then dendrohydrology, the scope is in this area. So, now last is the tree is the faithful recorder of environment. Any change in environment that is recorded by tree. Our skill is how we extract the GIC. With this, thank you.
Questions?
You already visited Aryabhata, right?
Yes.
Sir, the graph you showed us of the Himalayas and the Himachal Pradesh, you were explaining the changes in climate. So, sir, it is due to the western disturbances are more common in the higher Himalayas than the Himachal part.
Yeah, actually, Kashmir is the little higher latitude, and western disturbance is one of the factors.
So, Himachal part is more prone to
Each monsoon type of disease.
Hello, sir. Good morning. So my question is, what should be the density of sampling if we select a patch?
So at least it depends on the how sensitive they are, and the minimum 30 is required. If these are not very sensitive, you have to again move and think how much. We are maybe some 3-4 kilometers there. But it depends. It depends.
Depends on the trees also. पेड़ कैसे मिल रहे हैं? It must be
Yeah,
depending
yeah,
on
yeah.
that also.
Yeah,
How big
How big,
and
how
how
big.
big.
Generally, we take the information from quality department. They know well, and where things are available, they tell us the correct things.
तो जो काराकोरम anomaly है टेम्परेचर की जो दिखती है तो यादव से किसी पेपर में ट्रीइंग से तो क्या वो और जगह भी कश्मीर से वो दिखता है anomaly क्या मतलब अपने लोगों का काम है
There is some anomaly. This is reducing.
climate change, global
But
warming,
I-
but that's
yeah.
moving.
But I agree.
So, when the trees are in their early age and in their old age, they grow differs. So, in Himalayan region, how is that different? Like
Growth in
in
the initial year and later year.
Ah.
The beginning of the growth of a tree and later years. So how?
The tree growth, generally, tree growth start by March. March to October. During winter, it is dormant period. There is no new cell formation. Growth means new cell formation. In winter, there is no growth formation. There is dark bag. Again, in next March, we start growing new cells. Initially,
actually, sir, like in the earlier age, like July time.
Generally, we don't consider juvenile part of this developed chronology.
So my question is, so you just show one slide in which the in eastern and western Himalaya you consider about 7 tree species for the dendrochronology, but in Western Ghat, teak, champa and so why this Torana? Okay. These 3 species are there you suggested.
No, those are not very good. All are target.
Okay, what is the problem? So in Western
Green also. Green is not distinct like conifers. It is different. And it's kind of distinct.
No, I'm not distinguishing, but why there are very few species people for dendrochronology in Western Ghat?
From tropical period.
Distinct rings are not there.
Distinct rings are not there because we need the annual evolution. Perfect.
This is this year, this is this year. All are same. Same means there is no demarcation. One ring to another. How do we know that this part belongs to this year, this part belongs to this year? So there is no dispute. So, for regarding the questions, it is evaluation what you have done in the this workshop. So it is for individual. So it is your sincerity. You discuss or you don't discuss. You use internet or whatever you do. It is your sincerity. It's up to you. You are not small kids. Okay. So you evaluate yourself and you take yourself and give marks and give it back to you. We are not going to evaluate. This is your evaluation. You evaluate yourself. You have come all the way from different parts of India. So it is worth, so you yourself evaluate, was it worth to visit this far? Okay. So this is the question. So it is not like we are giving marks and there will be some award. It is not like that. So you evaluate yourself, give marks and submit. That's all. So it is up to you to how you handle this.
2 marks for each page.
So, I thank Dr. Burgaonkar, and so we'll go for a quick break for tea, and then we'll resume talk on the statistics and the methods which we use in the paleoclimate. Now, sir.
Students, please listen. We expect you to write your answer there. ये सिर्फ आपको पढ़ के मतलब दिमाग में आंसर हमको आता है नहीं आता है वो नहीं करना है. We want to see you write what you are writing there. Okay? So you have to sit, spend about half an hour and write it. Okay? So ये नहीं है कि हाँ मैंने पढ़ी ना मुझे आता है. यार मैंने सुना नहीं. It is, that's what we said. And if you think you can't evaluate yourself, leave it. Don't evaluate yourself. But whatever you think your answers are, please write them there. Fine? After Kalinda's stop. After Kalinda's stop.
It's not a
After that, surely. Yeah, okay. We shall end it at the end of the day. When we compare with other how much? एक मिनट भागना भाग हम लोग को भागना है थोड़ी देर में करमल सर आएंगे हमको रिसीव करेंगे क्या
Hello, welcome. So this is the last lecture of this workshop, and so here is Dr. Annapur Reddy, Phanindra Reddy. He did PhD with me in IITM on speleothems, and the most challenging part of the paleoclimate data are like they are unevenly spaced, right? So because any like in sediment core, lake sediments, or the sedimentation data are not constant. It varies with time. So and that we don't know a prior. Where by seeing the maybe sediment core, some cases you can visualize, but you cannot concretely estimate what is the sedimentation rate, or even like in speleothem, how it grew in the past and what was the growth rate. You don't know. So when you for what you will do is you will pick some sample at some intervals where you see that there are layers are good, or in the sediments also you look at maybe there may be some event or something, then you pick some the samples from there and then you send for dating. So when date comes, then you find that there are some intervals where the growth was very, very fast, or sedimentation was fast, somewhere it was slow. So but the proxy you are looking at, you are generating some data, for example, biomarkers at some equal intervals, or like forams you have taken with some equal intervals, maybe every 5 centimeter, 10 centimeter or something. Like in speleothem, you have taken at every 100 micron. That is the distance is constant. So, but how to translate that your ages you have found with the variable growth rate or sedimentation rate to these numbers? Okay, so it is not very straightforward. So that's why we use actually Paleoclimate committee, they often use age models where the age uncertainty as well as unevenness in the data have been translated, those errors have been translated into your proxy data. Okay, so he will teach you and how to handle those unevenly spaced data set to get the information about the what are the periodicity embedded in the data, and then you compare those data sets with the other climatic parameters to find the causative effect, right? So okay, to Phanindra.
Yeah, I may not deal everything in this lecture. However, I'll try to show some of the information what I can complete in this talk. So first I'll be dealing with the Copra age model. You might be knowing what is age model, and if you have a sedimentation rate, if you have a sediments and then you have ages different at different depths, you will be having ages, and ages have uncertainties. Okay, so when there are age uncertainties, how you will be dealing? That's what the model this model will do. There are several models. So there are several age models. One of them is best is which uses the stochastic nature of. Okay, simply speaking, it will use standard distribution of a data set of your ages. Those ages uncertainties, it will be translated to your proxy uncertainties. Okay, so maybe I'll try to be simple. So slideshow.
Full screen. Yeah, there is an option. Make. Second one,
That is white screen.
oh,
Okay.
To share the whole.
okay.
No, this is okay. Probably this will work. So these are the recommended literature. So one of my favorite is if you want to understand anything, like if you want to do any statistical analysis, best book maybe you can go through is this book, Simpson and Kafka, and we will be sharing this information. Will be. Then this is the one which I'm talking, age model, Brighton back in 2012, and their team they have their team have done this age model, and which is available in different aspects like MATLAB, Octave, and Python also, better IDF programs, and then Spectrum, which is Sculge and Statager. They have designed a paleoclimatic based spectral analysis tool where you can directly use unevenly spaced data, and then you can employ these spectral techniques directly on the unevenly spaced data. So you can get the spectral content in the each at different intervals. And then the Redfit is also one of the technique where this is enhanced version of spectrum. In the spectrum, which you don't have is a red noise, like you cannot distinguish, you don't have a false alarm levels. In this, however, chi-square false alarms are there in a spectrum. In Redfit, you have a auto-regressive function where you have a red noise, so you can use those your false alarm where you can check the peaks are good or not, like are they satisfying your conditions or not. This is another paper, similarity estimate. So these we will be sharing, and in this book chapter we have exclusively discussed different spectral techniques where it can be used, and what all these spectral techniques have a different approach. Like one of the data set has a feasibility for one of them, so you have to employ those spectral techniques based on which you want to use. So yeah, maybe I'll just go through this quickly. Frequency is something like it's not time. Humans think that it's a time, not actually exactly speaking, it's not time. Humans, everything understand in the based on the frequency. Maybe I don't know. You understood all that? Yeah. So this is the central tendency, mean, median, mode. These three things are like earlier what I mentioned, frequency and this mean, median, central tendency. These two are sufficient enough to understand the basic concept of statistics, and you can apply there. And we always think that these are not at all sufficient. Like we overlook on these. Actually, these are the most important. Mean means actually it's a balancing point. So the mode means it's a frequency, number of times it is repeating. So the median means it's a central, which actually central tendency means it is actually in the center. So these all are sufficient enough to understand actually most of the first order problems in our time series analysis or any of these things. So coming straight away to the age model, see, I have this is a schematic representation of a speleothem, maybe like those dotted lines are growth layers, and as we see that these are these. Let's assume these are different uranium thawing date samples where we have collected, and that is T1 is the time age after getting uranium thawing dating, and E1 is an error, corresponding standard error. And this is younger and this is older. So what we will be trying to understand is if these are having different how growth rate has been as Naveen sir was mentioning that how we can use this age errors can be.
How do we know that there was a hiatus at that time?
Yeah, that is a question I would like to ask people. Like morely hiatus means, as we see from the growth layer itself, we can see that, and you see there is a large age difference, very large age difference, and definitely within that short range, if something happened like 1,000 years, nothing sediment has not happened. One of the way technique is to understand that way.
So then you should have a closely spaced dating.
Yeah. That is not so easy. Yeah. You need almost some grams amount of grams to do that. So this is from Brighton back to the fall paper. I just used that to just show you how hiatus looks like and how these hiatus and age reversals. You can see age reversal. It's not monotonically growing, right? So there is an age reversal. This point is an age reversal. No? You got it? No?
So it's zoom in a bit, you can't see properly.
What?
It's not visible to them. That's okay.
So okay, maybe I'll zoom in later on. In the paper, I'll show that. I'll zoom in. Right?
No, they were just asking if it is possible to boost it.
So this will be sharing that with you. So you have to download. I'll just give you how to deal with this thing. If you have any specific question, better you can write me. If I know, I'll just give the information. See, download. It's everything is clearly mentioned in that website. You download that file. Those two files are that MATLAB files, and then you add a path. You add the path to that where the folder is, and there to the MATLAB. Then you run these two MATLAB files, and then you are good to go. Like then in the MATLAB, you open MATLAB, and where you can type Copra GPUI. If I have time, I'll just show you how to do. It's not at all a very hi-fi thing. It's just simple thing.
May I know, actually there are already several existing age models, right? There are Bacon, there are Oxcal. So what is the advantage of Copra over? Is there any advantage?
Yes, it is there.
First question.
Yeah.
And what is the major advantage over other existing age models? So it's,
see, earlier models, they are not translating the age uncertainties. Actually, as we for example, if you have age some 100 years plus or minus some 10 years, this is the standard error. So this standard error, what it will do is they will consider this as a Gaussian curve. Okay, they randomly pick one of the data point. For each depth, we have a different age interval. There is an image, I'll show that later. So for every depth, they randomly pick. Okay, they do Monte Carlo simulations. Now you got for each run of the Monte Carlo simulation, we have one particular proxy value assigned for entire your thing. Your spillover, like at each for each depth you will be assigned that. And then for 2000 simulations you have 2000 different proxy errors, and for 95% when you have seen that, and you can easily exclude if there are no variations in the 95% of both the sides, then you can easily exclude the climatic extremes. There is a variation or not, you can exclude it. So none of them earlier has translated.
What you are trying to mention is that this Copra model essentially translates the age uncertainties
with the proxy uncertainty,
which may not be the case with other
things.
Other Bacon or of course with Oxcal, they will be
simply you will get a one mean value. So one mean or one median value, but as we just now shown that the mean, median, and mode are not always same. Like we should be dealt with carefully.
Actually, it gives the full spread. Mean would be some, and then it will give us, maybe you can choose 95% or 98%. So it will give you in the top of below and top, you will find a way, and there will be some change in the peaks because your age has an uncertainty.
Yeah.
So that So that is the advantage here.
Yes.
So you just need to load the data in a text file where three columns will be there. First column is your depth versus age, and then uncertainty in the third column, and where you will be loading them. And then load your proxy data. In the proxy data, depth versus oxygen isotope or proxy, in any proxy, 13C or anything. And then if you have a lamina count, as we see, I don't know, you can see it. There is a lamina count is there. If you give a lamina count for a particular depth, 30 mm to 40 mm, you will get a good resolution.
So is it only applicable for stalagmites or for
any sediment?
And the input we gives, is it the uncalibrated edges or the calibrated edges?
Calibrated edges. We give the calibrated.
So we have to calibrate it using a different program and then have to provide it to the copyright model.
No. If you have already calibrated edges, you can give it directly.
So what we get from a lab actually is a raw data,
okay.
And we usually tend to calibrate it using various programs, what I suggested, Oxcal or there are.
So for this you have to give
calibrated
edges.
Expanded error, maybe 1 sigma 2.
So then in a Copra model, it looks as if we have to calibrate it using a previous, for example, in lake systems or any other. For here in uranium thorium, it may not be a problem, but for 14C date, what they give us is an uncalibrated date. So we have to calibrate it and then has to provide it to the corporate.
And we accept all types of data, either biomarker or just medical data.
You just need depth versus your proxy. That's it.
Calibration curve is available
With Copra. No,
calibration curve for
like for example, like INTCAL and all these things for 14C dating. There is no calibration curve. Then that means you need to calibrate the dates and you need to put a values here.
Yeah. And then that is how this age model looks like. No, not age model. Now it will ask you that do you, if you know the concept of, is that really the ages are proper ages, or is there any age reversal? Like as we know that speleothem grow monotonically, right? Or any sediment normally grow monotonically, right? So when there is an age reversal, you must be knowing from your uranium thorium date like excess thorium content, or you can visually see that it will not jump like that, right? So what we can do is in this program.
You explain what is age reversal? Anybody understand? What is age reversal?
Typically, if the age is like inverted.
For example, like the bottom one is the oldest one. Say in sediment course, the bottom one is the oldest and the top one is the youngest. So if you date, it should look like this. But all of a sudden, in some particular layer, it looks like it's it should be older, but it looks like younger. That is called age reversal. And it should be other way around, but it looks reversal. So the changes would be the cause would be very different. Like in sediment core, maybe sediment got disturbed, something like that, right? I mean, in speleothem, it is possible that some detritus thorium might have gone there. In speleothem, what we see is the decay of uranium-234 to thorium-230. So we are assuming that there is no thorium-230 at the start. So, but it's possible sometimes, we don't know, nature many things happen. So if some detritus thorium has gone into that layer at the beginning, so it will give some bad thing. So that's why we mentioned that you do some chemical analysis first to check the layers, so the thorium concentration, uranium concentration, there are the checkpoints. So there you can discard that data. Because discarding anything just because it is coming there, you are discarding it is not a good idea. So, ethically, it is not correct. You should have a strong basis to discard something in your data. It is not like, okay, it is not suiting it is not my story, so let us discard it.
So there is a general tendency as well that, okay, your age model, whenever you are constructing an age model, there will always be an obvious outliers. Because, of course, in a natural system, as far as 14C dating is concerned, you can have reworked the organic material which are coming. And of course, in a carbonate system, you can also have reservoir effect. So there is always a general tendency that we exclude the dates which doesn't fit our car, right? So don't do that. So you consider them as outliers, and make genuine, try to assume that whether it could be a possible reverse elements coming into the system. So try to interpret in that way. That's what Naveen is also trying to.
Look at the other data sets and look at is there any some anomaly in that particular near to that. Based on that only you keep them as a outlier. So this is what it is here.
Better if there is a replica or anything next to it. That is the best way to you want to remove the age or anything. Better you, but it's not so easy always collecting samples, many samples, and getting the same age. So here what I see is there is spread is more, as well as we found out that there is uranium thorium content is more. So based on those conditions, we removed this excess thorium content is the main thing. So we removed that points. So you can give those numbers if whichever you don't need it, if according to the conditions, in climatic conditions. So you just type the number like 6, 7, 8, and comma, and you can just get rid of those things. Then you have to run the. There is an option after you removing that. There is a construct age model. It will give you an age model where it will be shown over here, and by running the 2000 Monte Carlo simulations, okay, the maximum you can go 10,000, I guess, and it takes a lot of time. 2000 is sufficient, and it depends on you, like how much you want to do. And it is showing there is a tractable age reversal. Yeah, it is not visible. So what happens is, I'll just come to that later in the concept. Then this is an age model after constructing. There is a spread. These spreads are related to the age errors. Okay. And then you can construct the proxy record using just simply, this is a graphical user interface. You just do everything, and the background codes will run, and you will get the data. And this is the 95% percentile spread of the proxy data. Okay. Then you can download, and you can do this if you want a mean data set. If you want, and it can be exported to the text file. It is so simple. No, not very. Now this is where the algorithm we should go. First, you have to give enter the depth age data, which should be in 3 columns. First column is your depths, and then ages, corresponding ages, and corresponding uncertainties of two standard deviations. So then it will prompt you, and then you should be giving the data set depth versus your corresponding oxygen isotope or the parameter what you have generated, and then it will ask for you the layer count data. So if you don't have also, this program will run and give you age model, and then if it is yes, and you can give it. If it is no, it will go to the reversal checkpoint. If there is an age reversal, that's what according to the conditions what you have specified, that age can be removed. Okay. So once you remove, and again it will ask for you, is there any hiatus and all these things. Then it will go to the it will check the points, and it will ask you again that are you satisfied with the model what it is generated. Then you go back and you can run always, and then it will accept, and you get all these data, and you can export the data. So these are the conditions, and these are the assumptions what they have taken. One of them is monotonic growth, and it will translate. This is a normally distributed random. I think it is there. I'll just maybe it is not having. I'll just show you later. So randomly it will take each age from the different depths. Okay. This is and then it will construct for you using the Monte Carlo simulation. It will construct for you one age model. So there are so many age models because of the more number of Monte Carlo simulation. Yeah. After that, let us go to the spectral analysis. So in the first left top panel, as we see that this is a equidistant space data set X, and there is a Y. For example, if you consider only we have X data, okay. in any instrumental data, you always measure, you give a frequency like okay, 10 seconds or 1 minute or 1 hour. So you get the data in equidistance manner. But as we consider in paleoclimatic data set, most of the data set are not equally distanced, as we all know. So for now here, if you want to compare, there are two data sets. For example, you have ice cream sales every month, and then every month you have temperature value of that location. So you want to understand, is there a relation between those two? If they are equidistant, and it's a straightforward answer, like we can just put it in XY, like these two things, and what will be the next month, how much we can get the ice cream sales and all. We can see by fitting this least square. What is that actually? It's a regression model, right? No, forward. What is this line? You fit a line to that model, right? First order regression model. No. Okay, what it does is you have data. So if you want to predict the next month data, so you should have a model, right? First order model. Let's assume this is the first order model. Y is equal to mx plus c. This you might have seen, you might have heard of this, right? Now we know y value and we know x values for this data, whatever we have. Now we have to know these two values, m and c, so that you can have a straight line where then after like y is what are the sales in 10th month, and if you know the m value, the x and the x value, you know that number of the temperature, for example, and you get the sales. Okay, so this can be done by, like, you minimize the distance between the you assume there is a line here, and there is a deviation, there is a distance, perpendicular distance, and you minimize that. That minimization will give you the value, actually y is equal to mx plus c curve. Okay, so the similar way, what in the frequency spectrum, what they do is they do you can see this, they minimize the distance, minimize this the original data what you have, and then the modeled frequency, modeled Fourier frequency. Okay, this is the spectral method. How it will deal is, like, first it will divide the 3 segments or number of segments, how many segments you want, like let's say 4 segments or 5 segments, better. They divided in 3 segments where it will be like 50% overlapping this data with the earlier data, and then they did a Hanning window. This is the paleoclimate data. This is the Hanning window. After doing the Hanning window, this is the time series what you have left with, and then they do the Fourier transform. And when they after doing all the Fourier transform, they average the periodogram, and you get the final Fourier transform. This is the paleoclimate. This is the original way of doing Blackman-Tukey method. So what they do is they do autocovariance functions, like, which is nothing but the auto correlation. In the earlier slide, you see the autocorrelation is with lag, some lag value. Okay, autocorrelation at 0 is 1. You must be knowing. And then apply Hanning window. Once you apply the Hanning window, it does look like this, and then you take the Fourier transform. So this is the Blackman-Tukey method, and for equidistance space data, and this is also Welch overlapping segmentation data, and which is used in this Kulj and Statler 1997. These are different techniques, different spectral methods where one can use for spectral analysis. So spectrum, Redfeed, and TS Aviso, and then Nest Toolbox Wave. This spectrum is like the which one I was mentioning. The same method is used in Redfeed, but however it will have an autoregressive function where it will give the red noise data. you can exclude based on the false alarm values. You can exclude the peaks or the periodicities are really there or not. And TS aviso, which uses a date compensation discrete Fourier transform. Those are like, once you read it, you will understand. The next toolbox is you have this Blackman-Tukey method earlier. So auto covariance function, what they do is they do the Fourier transform on the autocorrelation function. Okay. Then Wavepal is which has plenty of options. Yeah, it is also using the same technique, Long's-Call Fourier transform only, but different false alarm, Monte Carlo false alarms also available on that. So based on your data set, what you want to see, you can employ those spectral techniques. And yeah, thank you. Maybe I might not put everything in detail. But
so there is a book chapter we prepared for comparing all these spectral methods. What are the advantages in one or other, and which method is suitable for which, so that you can go through and when any difficulty you forget, right? So
there are parameters like actually
you don't need
see maybe in person to person also maybe I can explain you better. Now we have a limited time, so I'll just at a glance I'll show you how to run this Redfit model. Yeah, I'll show you once. We have sent a mail to you everybody where there is a link for these spectral methods, at least spectrum and Redfit and cross spectrum Redfit only. Those methods are so easy. You have to analogously understand. It's not like so much of mathematics are involved there. So you can download these things, and it is just export and extract them, and then go to command prompt, and you go to the file where I'll show you that. Yeah. Now you see this Redfit X means cross spectrum, and there is a zip file. You extract them, and you will see this Redfit configuration file, where it will be having like this. Okay, input data where in the text format. Okay, then it must be in one column. It must be your ages and corresponding value of that parameter. Okay, and then if you want to do okay, this is not a cross spectrum. This is only normal spectrum. That's what it has, only one input. So where you can do number of simulation, Monte Carlo simulation 2000, and it is asking Monte Carlo test, do you want to do true? Yeah, yes or no. And row value should be -99, and AFAC and oversampling factor, it is 4 here. Highest frequency, the total, and are you taking the total length of the data or not? Like, yeah, we are taking entire data set. How many number of segmentation that I earlier showed? Those segments, if you overlap now, once you overlap the data, you will be so confident that there is no if periodicity is translating from one place to another place, it is clearly seen from them.
Segmentation means your time series you divide in 3 parts, and you divide in 3 parts such that this part and this part has a 50% overlap. This part will have a 50% overlap. Then it will compare. But otherwise, in simple autocorrelation, what it does is take this and the same curve, you just move. Here, what they do is they make a segment, 3 segment, 5 segment, depending on the length of data. And those segments has a 50% overlap. That's all. And it moves because it is animally displaced data set. So based on that, they do hanging window, then they do the spectrum.
So these windows are nothing but something like there must be a spectral leakage. If there is a leakage, spectral leakage means see if there is a continuous what is the energy of any frequency like a periodic signal? It's infinity actually. If there is a periodic signal, it's keep on going, right? The period is infinite. The energy will be infinity. Its period is something like the sinusoid wave. It is keep on going. Expansion of sinusoid, you know, x square by minus blah blah. It will keep on going. It will not stop. But we are truncating. Something energy will be always it's keep on infinity. So that energy in the periodogram, but your spectral density will be constant. That is what it can be done here. Any
which method we should? I mean, which?
So that's what in that chapter we have.
So you have already mentioned.
We have already mentioned. So what happens is if you change the off-air value and number of segmentations. So what happens is the frequencies will overlap.
Okay.
If there are the energy will overlap actually. This is had seen earlier very long back. So they to remove that means if you want to separate those frequencies, and sometimes the spectral peak will also change from one location, like it shall be 20 years periodicity it will show, sometimes it 24 years periodicity. So this change will normally it comes from this opaque and number of segmentation. So we should be better. We should know the yeah, like causality. Causality is the best way to like why it is happening. Like 11-year cycle we already know it is from sun. So sometimes there are certain period 22 will come. So maybe 11 multiplied by 2. This is harmonic. This could be a harmonic. Like we don't know which one is what. So now you should be having confidence enough to is it really a harmonic of a solar cycle, or is it 22 cycle is there or not? So based on those things, we like it's our interpretation.
Actually, it's a past.
Yeah, past is also uses the Foster. This TS Aviso I was mentioning, TS Aviso. Foster 1994.
Same parameters. You can change all the parameters and then you can do the spectral analysis. I mean, the red spectral analysis, wavelength analysis, everything is there.
Yeah, everything is there, but actually it's a black box. You cannot change, modify any of this.
Exactly. Yeah.
You don't see whatever it is giving. You have to like okay.
Yeah, exactly.
So it's I'm not discriminating, but it's like
yeah, I can understand.
Yeah, this you play inside, like you change things and why it is changing and why it is not changing. You can do that. So this is TS Aviso. Actually, yeah, you can read that chapter maybe. I recommend if you're having more non-linearity in your system, better TS Aviso is a good one. If there are signals, if your periodicities are matched, this is a you can false peaks you can remove manually. You can see you do iterations. It's TS, but that they have stopped. This is from NASA. So if you want to, okay, you understood this. So the basic thing, correlation.
No, actually, there are methods which only give your periodicities. If you are okay with periodicities, you choose.
Just spectrum or Redfit. Redfit is best thing. Okay, Redfit have all these. Many people use Redfit.
Redfit is the best or spectrum?
Easy, even easy, and you can do many things.
It is very easy to handle. But if you want to do more rigorous statistical analysis or like coherence spectrum, wavelength analysis,
wave path,
then you go for wave path method. So you need more some better computational knowledge. So it depends on. That's why we in this PhD we did this entire exercise, and in the book we actually prepare a chapter to discuss all these things. So we will share that chapter, but it's
I will not discuss everything.
Then you come discuss, right? But until you use it, you will not have any problem. to ask.
I understand. I will not
Take some data,
put
run it,
my things.
then you find problems. Then you ask.
They want.
Is there any way to like a cross correlate between two
This is
unequally
why
spaced?
that is why the paper, that is a point.
Next toolbox.
Data are unevenly spaced. So you go for wave path.
Cross correlation.
Yes, yes, cross correlation, yes. It can cross correlation, everything.
For that case, can it be like be in the same age model? Like can the two data are in the same age model to cross correlate between these two data? Like from one data from Central India, another data is from North.
Those so.
This method will do cross correlation for any data, which are unevenly spaced.
Another question is, so what is the difference between this copra and the Stallage model that we have previously used?
Yeah, Stallage, that's what he asked. No?
First question was this, right?
So you cannot translate your age uncertainty. You will get, so did you run the Stallage model?
Yes.
So do you have a proxy error? You have a median, only oxygen for a corresponding depth.
That is also like the working the same, like 95% confidence level, and the Monte Carlo simulations it is taking.
No, so the point is, see, the point is.
No, it will give you new value with some confidence.
Assumptions.
Some confidence is there. But the point is, not translate age error into the proxy record. It will give you your age model and it will consider in the age error. The age model only you will get 95%. But the output in your data value, there will be no effect on that.
See, even Copra, the
Age error will be only reflected in your age model. It will not translate that spread into your data. Here it does both. It takes care of the age error because some places you have more error. Some places you have less error. So it will take care of that. This method will take care of that even constructing the age model. Then wherever you have very robust agents, so it will give more confidence. Okay, then it will translate that confidence into your data. But that is missing in the previous
See, in that Brightenberg paper, they have clearly defined why this is the best one, and even they quoted whatever you are asking, the Stallage, right? So the Stallage doesn't deal with these age uncertainties to the proxy uncertainty. Like, so the proxy will also have an uncertainty, right? How you are telling this is the mean means proxy is the same. If you have, logically, are you understanding? If age has an uncertainty, why not proxy? Age means what, man? Age means it's a sedimentation. Where at that particular age, its age itself has an uncertainty. So, if you want, personally, you come. I can just.
Times maybe today or tomorrow. You take any times and you give them some. Maybe you can send.
I already sent. Actually, I already sent. If you want,
send them some data set. Okay, in one column depth, second column age, third column this, and then there is another file will have it depth and proxy data. Then you yourself run. At least you do at least age model. Okay, everyone try.
If you have age, if you have a model, I mean, any data set, you just show me. I'll do it for you. And we can physically, if you have uranium thorium concentration also, we can remove, and any physical signal is also there. We can remove that. This paper seems to be so mathematics. We always avoid, but actually they clearly explained it.
Sir, while calculating the periodicity, in bold that North Atlantic Constellation, they have given the ages of around cyclicity of 1,000 or 1,500 years. Like in some
data sets of China, they have given 500 or something like periodicity. So if we are calculating like the Monte Carlo simulations we are running, if we are taking at 70% or 80%, 85%, 95%, they all will give different results. What would be the which periodicity we will take that this is the periodicity of this cycle? After this cycle, the event will be.
So here Kriplanisar is not there from IITM. What he says is always statistics is a tool that you can prove anything and you can disprove anything. It's off record.
No, but actually, when you're comparing some two, like this is actually some other previous paper. If you want to compare, right? So you sometimes what happens, you run the your code, you will get some periodicities or then you will see whether these things are there in the previous year or not. So the problem is they have used something else. So better what you do, you take that data and run that. You make everything on one platform first, then compare.
No, sir, I'm not comparing with them. I'm saying that
you are confused about the periodicity.
That's what I'm telling you.
Right?
Those periodicities you are talking about. First, you produce those periodicities using the same data based on what. Are you getting?
Yes.
So there is a mathematics has evolved. Computational thing have evolved.
Their data set also, my also.
Yes, using the same code. Then only compare. Otherwise, they have used some different method. So maths will give you all sorts of periodicities.
Yes.
Right? So you bring everybody on one platform and run your own code, then compare. Otherwise, just quoting other thing and comparing, then you will doubt. Then you will say some new science you will bring without bringing everybody on the one board. So that's why in that food chapter he used all the data sets which are available and run all the data set on one program. That is the best idea to do it.
So that Redfit is there, right? This is simply, you just don't need so much thing. Like this is also very easy. What they did for us is in the configuration file, I just shown that you have to change all these input values. This is an output file. This is the path, just a path, and .txt file. You name it, whatever, and number of simulation and these things, everything. This is a window. Each window has its own advantage and its own disadvantages. Like how the spectral leakage is happening or not, it will show. And better, it's depending on the problem. Better, sometimes Hanning window is the best, what they say in the Paleoclimate, and many other things also. So you just save this file, and this file, configuration file, and your data set. Yeah, you can change the data set path also. But this Redfit .exe, this Redfit 38.exe file and configuration file should be in the same folder. So just run. Done. You got your data. And in your file, wherever that file is there, they are clearly mentioned what is the column. Header file is there. What I mean to say, the header file. That each header file will give you the each thing will give you what is there and what is not. Okay.
So what you will do today? So we will wrap it up.
Yeah.
He will send you some sample data. Okay. And he might have forwarded you some link or the code download. So you yourself try. Okay. So tomorrow we have a whole day together. Right? So you ask. What is, I tried this, I could not find this. So this way you learn. Otherwise, it is not possible. And this can be learned only by doing it. Right? So today you try. Okay, 2-3 people sit together and try one laptop, and he will send some sample. Okay. So we will move to that hall. So we'll thank first. So we will move to the Varamir hall for your certificates.
distribution. So we have to be quick because our key guests have come on. Sir.
This paper, you highlighted something. I saw that you highlighted something. Also, how to mention plow at all. That plow is you are telling that. Even the style, his problem is also clearly addressed in that thing. See, I was when they come to lab, I played with them. Now I couldn't. I don't know.
So the cross-fit correlation. So can we do that producing wavelet of one data and wavelet of another data, and we can cross correlate?
Yeah. So you are talking is something like convolution.
Yes.
See, you know this in mathematics.